Hello, everyone. Welcome. This is the last session of the Quant University Summer School Speaker Series for June. I'm very pleased to invite Dr. Jochen Papenbrock from NVIDIA, who has been both looking at the research angle on how do we make sure that we build an infrastructure for responsible AI, but also has been looking at pragmatic aspects of how do we bring in various tools and computing frameworks to build in trustworthy, responsible AI, primarily focused on financial services. For people who are joining us new, welcome. This is the Quant University Speaker Series. As many of you know, Quant University started out in 2013 with the goal of fostering innovation and democratization of various aspects in data science, machine learning, and finance. We work with various asset managers, large banks, large credit rating companies, focusing on the intersection of data science, machine learning, finance, but also looking at the themes of model risk management. How do you automate various techniques? How do we validate various algorithms? And in that realm, we've been putting together various educational programs to foster the thinking and also to make these tools accessible and pragmatic. In the last year, we have hosted 4 schools, winter school, an autumn school, summer school, and also a spring school. And we have had the pleasure of inviting more than 40 speakers to our Quant University Speaker Series. And they've shared their various thoughts on innovation and bringing in pragmatic aspects into responsible AI within the enterprise. And in that realm, we are pleased to invite Dr. Jochen Papenbrock to today's session. As you know, we are in the midst of summer school, and we have 2 streams of courses going on. The first course stream is a boot camp on machine learning and AI for finance. And here we are taking a deep dive into looking at the various algorithms and the methodologies, and we are building and automating machine learning algorithms. And the second series is a series on risk and AI. And here we have 3 courses going on. 1, risk and machine learning models, stress testing, scenario testing, and evaluation. A second course on algorithmic auditing of machine learning models. And the third course on model risk management for machine learning models. Now, these courses are in, we are holding it in partnership with Premier, and we're very pleased to have their support. So today, I'm going to introduce Dr. Jochen Papenbrock. So Jochen and I, we know each other for a couple of years now. And as many of you know, Quant University is an NVIDIA Inception AI accelerator company. And we've been doing multiple projects to make sure that many of the things we do are pragmatic and are also scalable. And in that realm, we have had multiple research projects with Jochen's group. And I'm very pleased to invite him as a speaker to this forum. And Jochen has both the pragmatic side to NVIDIA and many of the innovation efforts he leads out there, but also he is an accomplished researcher, and he has been working with various researchers on various themes, and he'll be presenting some of the work he's been doing with Munich Re and also with various forums. And in the third discipline, he's been hosting various research forums and frameworks throughout the European ecosystem to bring in experts from Germany and other European audiences, especially in today's day and age, wherein AI regulation is becoming a very important topic of discussion. So he has been working with GAIA-X and FIRM and various other organizations to bring in like-minded thought leaders and also startups and various companies in the ecosystem to jointly put together efforts to make these techniques pragmatic and operational. I will let Jochen start with his discussion in the next few minutes, but I also want to remind you that we have another session next week on Tuesday at 12 p.m. East Coast time, and then I'm going to be talking about algorithmic auditing for deep learning models. And the week after that, we have Hirsch Singhal from Wells Fargo, who's going to be talking about bias, fairness, and accountability for AI and machine learning models. So if you're interested in joining in any of our sessions, please register at q.academy, and we'll be sending out emails about future sessions too. and you will be able to access today's recording and all the recordings of the prior sessions in this training here. So let's get started with today's session with Dr. Jochen Papenbrock from NVIDIA. Thank you.
Thank you, Shri. It's a pleasure to speak in your event series. I have seen the speakers before me, so I'm really honored to be part of this today. So my talk will be about computing platforms for trustworthy, responsible AI in financial services. Before I start, let me mention that views are my own and do not necessarily agree with the views of my employee, NVIDIA. So just as a brief intro, so the audience knows who the speaker is, I'm in the board member of an EU Horizon2020 project called FinTech, where we look at the risk of AI in financial services and developed a number of use cases with several universities and discussed these use cases with financial supervisors across Europe and with the financial service industry. One of these cases, by the way, is elaborating on explainable AI, and I will come to this use case later. Also, in our journal, we have several research topics started on explainable, trustworthy AI, but also synthetic data generation. So all these topics that are relevant these days in AI in financial services. I'm also a topic leader in the GAIA-X project, which is the European sovereignty and cloud project. And I'm happy that you already enriched our talks and that you also work on a use case with us here. So it's very much appreciated, Tree, your input that you gave here in our GAIA-X project on algorithmic auditing and building trustworthy AI. I'm sometimes publishing in journals, for example, the Journal of Financial Data Science, and the first use case that I will present in a second will be based on some of these publications there. So currently I work at NVIDIA. NVIDIA is the leader in computing platforms in AI and high performance computing. And my role there is to take care of the relationships to our developer communities and our partners in financial services across EMEA. And but I'm also engaged in some of the global teams, the US teams, especially around trustworthy AI and explainable AI. So let's move on to the use cases. But before that, let me briefly introduce what I'm going to talk about. So first of all, the explainable AI use case with Munich Re Markets and some other colleagues who contributed to this. Then I will outline some extensions of that approach. Those extensions are both algorithmically, but also on the hardware side to accelerate things. And then I will discuss in the third bullet here about compute platforms and their benefit in bringing AI models to production at enterprise scale, and also the ecosystem around that and the benefit of open source for deployment and utilization and production of AI models. And last but not least, I will briefly touch deep learning and NLP, because that is also something that is strongly accelerated by computing platforms to increase the accuracy of those models and to be able to train them in a better way. And I will show some examples. So let us move on to the first use case here, which is a collaborative work with the team at Munich Re Markets, headed by Michael Ege, and also his colleagues Markus Jäger and Stefan Krügel. There were also other members in our team, namely Dimitri Marinelli, and also Professor Peter Schwentner, who works at the Institute of Wealth and Asset Management in Zurich at the Zurich University of Applied Sciences. So this is basically the team. And we spent several months basically on this topic. So it's a larger research agenda here, but also with practical implementation. And we were focusing on using explainable AI or interpretable machine learning for diversified, robust portfolio construction. So how to use that to come up with more stable, more transparent way of constructing investment portfolios. We also presented this topic around the GTC 21, which is one of the largest AI conferences hosted by NVIDIA. And the team around Michael Eger from Munich Re Markets, they presented their work and our joint work here at the conference. Also, we were able to publish our work in the Journal of Financial Data Science with actually 2 papers at present. The next one is coming up in a few months, and we will share the links to those later. So this is the screenshot of one of the papers. So here we call it more correctly interpretable machine learning for diversified portfolio construction, and you can download the PDF. So it's free download here. So the main idea of our work is to use a new sort of portfolio construction algorithm that is using network filtering or clustering, which stabilizes things a lot when you have noisy correlation data. So for example, here on the left-hand side, you see a correlation matrix of a multi-asset investment portfolio made of daily asset return data. And there are techniques to erase some of these information and to the benefit of revealing an underlying connection structure. For example, using the minimal spanning tree here, so this structure here, or using something called hierarchical clustering, like you can see at the bottom. And these are basically techniques that help you find the underlying complex relationship in such a complex data set. Financial markets are definitely a complex system, so you want to use things like graph analysis and network clustering. And we use this extracted structure here, like a dendrogram or hierarchical cluster, to come up with a portfolio construction rule or algorithm in this case, a very simple one actually. So we started in 2011 with an approach called hierarchical equal weight. So as the name says, we just put the weight in splits, 50% left-hand side and right-hand side at each intersection of this tree, all the way top down to the individual asset level here. So this is obviously a very simple scheme to acknowledge the hierarchical structure, but what's really missing at this point is the information of the idiosyncratic risks or individual risk of the assets. And there's a very simple scheme out there called risk parity, which basically attributes weights to the inverse of the risk, inverse proportional. So that idea combined with a hierarchical tree structure is basically the paper by Lopez de Prado, 2016. And he calls his approach hierarchical risk parity. So it's really like using the tree structure and allocating the weight according to the risk parity principle at each nested cluster, basically. I will come to these steps in a second. And in our analysis or our paper here, we compare this new approach, hierarchical risk parity, with a standard approach similar to risk parity called equal risk contribution, which also takes into account correlations. The big difference here between the two approaches is that equal risk contribution approach uses matrix inversion or optimization of the matrix, which can lead to huge problems when your data is very noisy. So, and this is also the findings of the paper of Lopez de Prado, published in the Journal of Portfolio Management 2016. Marcos uses synthetic data with specific shocks and systematic or systemic shocks to test and stress the portfolio. And the finding is that hierarchical risk parity is quite stable in compared to the peers like risk parity or minimum variance. So the out of sample stability is better. The target volatility is met in a better way. There's lower realized variance than the original minimum variance approach, which is really a very interesting phenomenon. So you can already see that using these kind of hierarchical structures bring a lot of balance, because if you change the data slightly, the input data, the minimum variance approach comes up with a very different portfolio, a very strange phenomenon. So it's much more stable to use these kind of hierarchical structures, because small estimation errors will lead basically to the same portfolios. And also it's a very intuitive way to construct portfolios, to allocate them to clusters and subclusters all the way down in a nested structure to the individual assets. So this may explain the stability of the hierarchical risk parity. So it uses the correlation data, but not in a way that is suffering from the noise of the data. It's a very promising approach, and just let me briefly explain the two steps of hierarchical risk parity. So you start with a correlation matrix, and then you have extract the hierarchical structure, like here, and you just rearrange or sort the rows and columns according to the structure, and you will already see these block correlation patterns here. And in the second step, you simply split your portfolio into two equal parts, and you measure the left-hand side risk and the right-hand side risk in terms of volatility, and then you allocate the weight according to the risk parity scheme, and you repeat this. So you split your portfolio again and again and again, and so that's the two steps. And in the end, you have your portfolio allocation. So we did this for a multi-asset futures portfolio. So we tested this with covering 3 asset classes: fixed income, equities, and commodities. We took a decent amount of daily data, around 20 years, and just to test what's going on and why this algorithm and what this algorithm is actually doing. And it turned out that we wanted to look not only at the empirical data, but also we generated synthetic data by a block bootstrap. So we had just many data set with similar distributions, so we could sort of Monte Carlo simulate our portfolio, and then we measured the outcome of the hierarchical risk parity, so the performance, let's say, compared to the standards, the equal risk contribution portfolio. So here we use, for example, the Kalmar ratio. You could also use the Sharpe ratio or any other performance, risk-adjusted performance measure. So we simulated 10,000 of these data sets and just measured the outcome in terms of the Kalmar spread. That's how we called it. And it turned out that hierarchical risk parity really dominates. So it's really has a very good performance in most of the cases compared to the benchmark. But why? So it was really, that's where our research started. Why was there this outperformance? We wanted to know more about that. So so we started to look at the properties of the data sets that we generated. So we started to measure the properties of the data sets of this market data and try to build summaries of the data set. For example, looking at the average return, the average risk of the assets in the portfolio, but also looking at the average correlations and other measures like how strong is the clustering structure prevailing and all these things. So basically statistical summaries of the data sets. So this was our input data for a machine learning model. And the output data basically is the outperformance of hierarchical risk parity over the benchmark. So to summarize all these steps, we had the 3 steps of first generating synthetically some market data by bootstrapping, then construct the portfolios using hierarchical risk parity and benchmarks, and last to measure the outperformance. So we have a labeled data set in the end. A labeled data set is perfect for supervised learning. So we applied a machine learning model, a very common one, the XGBoost approach. So it's a tree boosting algorithm that we use to train our model. And then was the interesting step. After we finished training the model, we wanted to deeper analyze what this model had found out, what the model has learned. So we use a methodology called SHAP or Shapley values, which is rooted in cooperative game theory. And it basically extracts the variable importance from a trained machine learning model. So in the end, we had the workflow of generating portfolios, measuring the risk and return, and in the end, extracting the Shapley values, so explanation variables, to be able to understand what kind of drivers lead to outperformance. And on this right-hand side chart, you could see the most important variables that our machine learning model had learned. So for example, starting here with the first one, it's a little bit encrypted what that means. So let me explain that in a second. It's about the maximum drawdown, so sort of a tail risk or downside risk of the futures in the portfolio. And we measure the maximum drawdown of all the assets. And then we were interested in what is the standard deviation across assets. So this basically summarizes how heterogeneous the risks are in our portfolio. And in a multi-asset portfolio, as we had as an input, it's clear that there are very different tail risks in these assets. Fixed income, for example, had low tail risk, whereas equities or FX or commodities would have higher tail risk. So we had very high heterogeneity of the risk in the portfolio. This was a driving factor of our machine learning models. This was actually the most important variable. So, and that makes sense because the more the portfolio is heterogeneous, the better the HRP works, because here is really, you need different levels of diversification, which the HRP provides. And then we could move on and look at all the other factors. So in the end, we really have the most important features extracted, which tell us basically why hierarchical risk parity outperformed. And we tested many data sets, also different ones, for example, with a low heterogeneity of risk, for example, just an equity portfolio or just another asset class. And there it turned out that hierarchical risk parity in some cases was not the most stable one. So we basically had an answer to the question, why and in which cases is the hierarchical risk parity a dominating and preferred strategy. You can extract much more information here. Also, you can extract like a sort of a local explanation. For example, you can just look at a single data point, a single data set, and really see what are the driving factors here. And also you can come up with some other interesting analysis of explainable AI. For example, here you can change the input feature and see how much it contributes in the prediction. So as you can see from these lines, our model has learned quite complex structures because it's not just a linear relationship. So we also see that it was useful to use something like machine learning and not just simple regression, because there are obviously some complex relationships present in this machine learning problem. So summarizing, we had the statistical properties of synthetic or randomized data. That was our input. And then we looked at the output, which was the outperformance of hierarchical risk parity compared to benchmarks. And then we used a procedure called Shapley values, which is able to extract the data, the feature importance information from a trained machine learning model. So it's a post hoc explainability approach. And with these information of Shapley values, we were able to see what is the really driving variables behind this. And we were able to see or explain, to a certain extent at least, in terms of variable importance, which are the most important variables that drive the outperformance of hierarchical risk parity. So this was an example to show how machine learning and so-called explainable AI helped us. In fact, it was just a more interpretable machine learning. Some people call it explainable AI already. in our case, we used XGBoost, as I mentioned before. And also we further process this data that you get out of this model in terms of explainability values. You can further process this in terms of visualizing it to really bring all the data sets to the table and analyze what the model has learned, what kind of cluster are prevailing. So data sets are clustered here. And for those clusters, you always have the same Shapley value distributions. So you know also which kind of data set groups lead to certain variable importance measures. So this was the base model. Basically, we published that in the Journal of Financial Data Science. And now we come to an extension because we were not so satisfied with the original block bootstrap approach, because in that approach, it's not really possible to get data that has completely different properties. And our model, our explainability model, it should be improved with more stress data or unusual scenarios and all these. So we came to the conclusion that we need a better data generating model. And obviously you can use different methodologies to get synthetic market data. Some people use agent-based approaches here. Some people use generative adversarial networks, for example, in the core GAN approach by Gauthier-Marty. You can see how they used GAN to produce correlated data. So it's all about generating synthetic market data in a univariate case. So you have one asset, or you generate data which is the multivariate case. So you're interested in generating correlated data. So how does this look like? If you look at the matrix here, on the left-hand side, you have an empirical correlation matrix from our multi-asset portfolio. And you see already the correlations and the block structures here. And on the right-hand side, you simulate or synthetically generate, using an AI model, these other correlation matrices. So they are quite similar, but like a human being or expert in this, he would not really see the difference between those. So I think Gauthier-Marty has an online test on his methodology, so people can rate if a certain matrix is real or fake, and around 50% of the people score right and the other half not. So it's a good test, let's say, that people can really differentiate between the real and the fake matrix. And the idea is originally to look at the stylized facts of correlation matrices. So if you look at empirical correlation matrix, it has certain properties and features. For example, the average correlation in these models is shifted to the right. Or you have something like a very large first eigenvalue, which corresponds to the market. And you have a number of smaller, but also still large eigenvalues, which could correspond to the industries you have in the portfolio, or the asset classes, or some other driving factors. And also, we observe a hierarchical structure in these financial market empirical data, and also some properties of the minimum spanning tree. So if you filter the matrix and generate a more like a filtered correlation network, this network has certain properties in empirical data. So the idea here was to have an algorithm that addresses these stylized facts at the same time. So we basically formulated this as a multi-objective evolutionary algorithm, and each and every objective corresponded to one of the stylized facts. So, so in the end, we used that algorithm and created synthetic correlation matrices. And once you have done that, you can use them to Monte Carlo simulate your data, and then you can repeat the entire process that I outlined before. So you can use this synthetic market data and measure the performance or outperformance of hierarchical risk parity. And then you can create data for a labeled data set for machine learning, for supervised learning, And after that, you can extract the explainability values, the SHAP values. So you can basically use the same process, but this time is enriched by a smarter way of generating synthetic data, synthetic market data. And the advantage also is that the multi-objective formulation of the problem of generating correlation matrices allows you to generate specific scenarios. For example, you could generate a matrix that has many stylized facts in the normal range that you see in the markets, but you want to additionally stress the pairwise correlation. So you increase that parameter and create a synthetic matrix based on these parameterizations. And then you can Monte Carlo simulate the data and see if what your model is doing and if it increases also the explainability. So that's basically a new framework that we presented here that can basically help you to understand any pair of investment strategies that in terms of outperformance. So you could also test what is the difference between the most diversified portfolio and the minimum variance portfolio, for example. So these are the two strategies that you compare, and you use the same framework here to analyze what is the underlying driving variables. This is an extension. Maybe I will skip just one short comment. The standard hierarchical risk parity, it uses a linkage or clustering procedure called single linkage, and there are many variations to that. You could also use other kind of linkage procedures and clusterings. And what we analyzed in this paper also is an adaptive strategy, where you look at over time at different time periods and have a measure or a criterion which clustering is the best one for which period, basically. So it's an adaptive strategy, and we are able to show that in certain constellations, this approach can outperform the standard hierarchical risk parity. And again, with the entire framework here that I presented, you can also analyze why that is the case and what are the driving factors behind that. And the third extension, and now we are more moving to the computing platforms, is about GPU acceleration. Because the problem that we really had so far was that the entire analysis that we saw, it took a long time to compute. So it was just one run with 100,000 data set cost us 3 days on a CPU cluster. So we needed to think about acceleration here. So we used GPU acceleration and were able to accelerate to 5 minutes, from 3 days to 5 minutes, because the entire problem that we have is embarrassingly parallel. So what does that mean? So how does GPU acceleration work? So when you have the code, you start basically with the application code here. And whenever you have some functions that are highly parallel, that's a good candidate to outsource them to the GPU, because in the GPU, on the graphics processing unit, you are able to run these procedures in parallel, compared to a CPU which you have in your notebook, which has, let's say, 4 or 8 cores. So you can only parallelize to that extent. In the GPU, you have thousands of these. So you can imagine what the effect is to use these. And this is the result. So we had the entire use case run on the CPU cluster. It took us 3 days. Then we used the DGX station with 4 V100 GPUs, which is not even the latest generation. That's A100. And we're able to accelerate to 5 minutes. So in that case, we used an open source framework called Rapids. I will later talk about this a little bit if we have time. It's like Python, but accelerated, basically. That's what we used here. And so the result was that the spec testing against synthetic data set, it should be the preferred approach when you develop tactical investment algorithms. And with this methodology here, you can quickly generate thousands or millions of synthetic data sets and run these machine learning approach and also explain what's the reason behind the outperformance. So it's really an amplified Monte Carlo backtesting, and we basically used a combination of smart algorithms that fit the problem, plus computing power to accelerate the problem. So in the end, the entire stack of algorithms and hardware really lead to this use case, and an asset management company or investment or hedge fund company or pension fund, they can use this on a daily basis and do a lot of experiments and stress their investment strategies and also simulate factors and using different kind of metrics and investment portfolios also. So it's a very useful machinery, I believe, for stabilizing and making things, for stabilizing the investment approach and to create more robust investment portfolios, and also to be able to explain what the more advanced analytics layers have actually computed and what was found out. So it's to a certain extent more transparent and also more human in the loop, because you are able to basically extract a narrative out of what you have seen in the data and the model. So maybe that's before I continue here to the credit risk management use case, maybe it's a good time to ask if there are any comments or questions up to this point.
So please type in any questions you have in the Q&A panel. I know there are a couple of questions which Jochen already addressed. So Jochen, this is fascinating work. As you know, I'm a big fan of GPU computing, synthetic data generation, and all the co-authors / researchers you have referenced in your work. The one question I have is with respect to synthetic data generation, and there's a lot of discussion on how do you validate these synthetic data sets. So what kind of a view do you have when you generate these scenarios, either adaptive or otherwise, either using bootstrapping or using some of the factoring in correlations and aspects? How do you validate these synthetic data sets?
Yeah, that's a very good and critical question. Let me just briefly go back to one slide here. So here in this very small font, I have the stylized facts listed. So, I mean, there are more stylized facts out there, and they are just, these are just the most prominent ones. And I'm sure we will discover more of these. And what we do in terms of validation is we just test our data, our generated data, if it meets a lot of these stylized facts at the same time. Because until recently, you had many algorithms, very smart algorithms that were able to generate maybe 1 or 2 stylized facts at the same time. Until the core-GAN approach by Gauthier Marty and some other researchers came to the conclusion that we need smarter algorithms that can simulate more stylized facts at the same time. So this, by design, we try to capture as many stylized facts as possible at the same time. So this is sort of our validation, but I'm aware that maybe there are more out there, or we don't really capture the entire thing. So creating synthetic market data is a really hot topic, but it's also a really hard topic, I think. Yeah. Right, and another sort of indirect validation is maybe looking at the machine learning accuracy. If it improves by more data, we can look at this, and also at the explainability. Does it make more sense? For example, is it more reasonable what the machine has learned? But again, I mean, we produce data that has never been observed before in the past, but you never know if it's going to be like that in the future, that's for sure. But it's better, I think, than just doing the simple backtest and the simple Monte Carlo, right? So it is a step away from the usual Monte Carlo approach.
Right, absolutely. Can I ask another question? In the context of the variety of data which gets generated, one aspect about whenever you generalize generators, you are more or less, generating data sets which the model has learned from the past, right? How do we factor in extraneous scenarios? Because ultimately, when we're testing it, we want to focus on the outliers which are possible, but may not have been realized. So how do you factor those extraneous scenarios which could potentially come in, which may not be very evident when you generate using traditional methods?
Yeah, I think I touched it briefly before. So one way would be to look at one of these stylized facts or two or three and maybe change a little bit. For example, you want to increase the average correlation and see what happens then, or at the same time, you think you need to test what happens if the hierarchical structure that you see is collapsing and there's less of hierarchical structure in the data, which is obviously something that changes a lot when market regimes change. So it's more or less, playing with the parameters, which still tell you something. So to me, it tells me something if I increase the average correlation. It tells me something if I increase the hierarchical level or structure. But that's the only layer actually in this model, at least, where you have some access to the meaning and can manipulate the parameters and get more synthetic data.
Absolutely, absolutely. Perfect. So I think if there are no other questions in the panel, let's continue. And please feel free to type in your questions if you have any, and we'll address it at the end of the presentation. Yeah.
Yeah. So the idea also was to before we came up with this asset management or investment management use case. Originally, we started with a different problem, which was a common one, like how to score and rate credit customers or loans in a credit risk portfolio. So this was actually the original starting point of our research on explainable AI. And this started in 2-3 years ago in our in this EU Horizon2020 project, FinTech, where we had universities from 20 countries in Europe involved, and also some startups and tech hubs. And we had basically many sessions and workshops with the supervisory landscape, with central banks, and also with the financial service industry in general. So with startups, with banks and insurance companies, to really hear what they think is the driving risk factors, what inhibits us from scaling in FinTech, what are upcoming risks and all these. And very early on, we recognized that the explainability gap is really a huge problem. And many central banks and supervisory authorities, they published on that. And we had many dialogues around explainable AI. So obviously, the SHAP values that we saw, it's also just a model, another model, right, with pros and cons. But it is, I think it's already a very established model, but it can only be just one out of many analysis and ways to explain your model. So Shapley values, they have the advantage to be rooted in this economic game theory, so that's a pro, and it has some nice properties, so you can interpret them. But also, I mean, explaining a model also needs to be done, or needs to be defined which audience, right? Is it the data scientist? Is it the manager? Is it the regulator? So that it's a very different field here. So we concentrated on the Shapley example, and we had a data set that reflected a portfolio of loans in a peer-to-peer lending problem. And so we basically executed the same procedure as before. So we know from our data set what are defaulted loans, what are non-defaults. So we could train this supervised model using XGBoost, and then we extract the Shapley values. The problem also here was that it took us very long time to do this, and increasing the data set to a Fannie Mae data set even increased the problem. For example, we had an 11 million data set, which was realistic compared to some banking portfolios. And the time to solution, or to extract these explainable AI values, or these variable importance values, it exploded on a normal CPU-based system. So it was, for some banks participating in our project, it was just not interesting to use that because it wasn't, the program couldn't be executed in a reasonable amount of time. So again, we used here the approach of the GPU tree SHAP and extracted the Shapley values. And the idea of the use case in this EU project was to, and I mentioned it before briefly, to further process the Shapley values with methodologies from network analysis, clustering, visualization, to better understand what the model has learned for validation purposes, for some more insights, for model debugging. Yeah, so it was really just another additional step in this end-to-end analysis that we added with the idea to not only cluster or network analyze the input features, but separately analyze the Shapley values. So the explanatory variables to cluster them and further process them. And here we could reach the same acceleration benefits. So on a normal setup, you could have an acceleration of factor 20 for the interaction values, which also are very insightful sometimes. So variable interaction values, the factor was even 200 or 250 or something. So you can really see that this end-to-end use case also has benefits when you accelerate that. And it starts already with reading the data. It's not only the machine learning or the SHAP tree explainer, but also all the pre-processing that you could do. So in the end, we were interested in end-to-end boosting and acceleration. And this use case now is more practicable for banks. And also we introduced this use case to this GAIA-X project, which maybe I have later a little bit of time to explain. So how did we implement this? And this is just a very brief overview of how we did this, basically, what is Rapids and how we did this. So NVIDIA is not only the graphics company, it's a computing platform company today. So if you look at our hardware, obviously, it accelerates things a lot, and it's not only the GPU, but it's also how things are linked and connected. So it's the entire hardware stack. And on top of that, it's important to have very flexible algorithms, and we have a lot of SDKs, so software development stacks and software for free that helps you analyze your data and accelerate these things like Rapids, for example, and data science. So you can use this in many, many industries for many applications, for example, conversational AI or many other things, also in the COVID research, for example. But in finance, obviously, we have a huge problem at the moment with these AI roadblocks. So, so everybody knows that we are in finance, we can use a lot of these AI models, but many people don't know how to start, maybe. So this is where this software or these SDKs, these software development kits and open source packages, they kick in at this place because they make things much easier today to implement AI. Yeah, so it's all about scaling. So if you have a platform like this, you can scale your models. So that means you can just make much better use of your data science resources, because the training and the inference is really accelerated, as we have seen, and you can run many models during a day, and also interpret these models. You have seen that interpreting a model also takes computational time and power. So that's really important. And also it needs to be flexible in terms of different architectures of deep learning, needs to be flexible in terms of the software stack, and also needs to be flexible in terms of where do you run your model. So today it doesn't really matter where you run it, if it's one of the big cloud providers where GPU are available, or if you decide more for an on-premise installation. And then it's really about a fast way to production. So this is actually what my colleagues and I are doing at NVIDIA to make the life of to remove AI roadblocks in finance, basically, and to make the life easier to implement your models. So, for example, we have here the usual process here. Data engineering is very it takes a lot of time. the data scientist needs to build the model and optimize, and you have many steps before you can deploy. And with our NVIDIA GPU cloud, it's easier to do all these steps. So the NGC, it helps you to use containers where everything is pre-built, so you can accelerate your loading and pre-processing. Then you can use pre-trained models. You have the SDKs, and in the end, you can deploy in a reliable way. So the time to production is increased, which helps a lot. And I saw this especially in this Munich Re Market use case, where we could accelerate the model and deploy it in minutes, basically. So this platform that we have is really, it helps you a lot, because also many others use it. A lot of developers on this planet use the more than 150 SDKs. And also a lot of startups use this. And that's also maybe a good link to our GAIA-X project. Maybe I jump to that at this stage, because we are running a little bit out of time. So let's go to the GAIA-X. Sorry for this. Yeah, so in this GAIA-X project, we have a lot of also startups involved. And this is also where Sri and I work on some of the use cases. So it's about basically a platform where we have synthetic data and where we validate and produce compliant AI, and also have an experimentation sandbox. And many of the use cases that we are working on here use this our software suite Rapids. So let's go to Rapids. And I mentioned that before. Rapids was basically the software that enabled the use cases that you saw. So it's just like Python. If you know Python, you use pandas, for example, for analytics, or scikit-learn for machine learning, or network-X for graph analysis. And there are corresponding packages in Python, which have different names here, but they can be programmed just like the Python. Only here and there, in a few lines of code, you change something, and you can then basically GPU accelerate all these things dramatically, and also scale across different GPUs with Dask, for example. The trick is to do a lot of workload just in the GPU memory, so you don't need to copy around the data. So you really have this end-to-end data science accelerated approach. And still, you can rely on your Python skills, and at the same time, you can benefit from this acceleration, and you are able to bring this to production. So maybe that's really the point where I should stop, just to give you an impression of what a computing platform can do for you, how it helps, how you can produce more explainable models, more robust models, and most important, how you really use them in production and not just in a POC stage. Thank you.
Thank you, Jochen. This was excellent. I think there was one question about, does GPU tree shape work with other algorithms apart from XGBoost?
Sorry, can you repeat the question?
Does the GPU tree shape algorithm work with other algorithms apart from XGBoost?
Yeah, so the XGBoost is the easiest one, because you can basically extract these tree shape values, which have very good and stable properties. But the GPU tree shape in Rapids, the shape approaches in Rapids, they can also be applied on any scikit-learn machine learning model. So then it's more like a kernel estimator. So it's more like an approximation, but still very useful and also very much accelerated. Yeah, and obviously you can also extract Shapley values from some really black box deep learning model, but at this stage you would need another library. So Rapids, as far as I know, is more for the scikit-learn machine learning models. So rapids.ai. So that's the website of this accelerated Python end-to-end data science suite. And also, if you go to XGBoost, you will also find the GPU tree shape, because it's already incorporated into that model. And in Rapids, you find the other methods that I mentioned. So yes, it works also with other scikit-learn machine learning models.
Thank you. And just to let anyone who's interested know, the Q Sandbox supports Rapids and it has everything pre-configured. So if anybody is interested in trying it out, let us know. We'll be able to give you a trial so that you should be able to run it on the cloud. You don't have to have a machine with GPUs available. They're going to provision an instance on the cloud and let you run the infrastructure. Speaking of cards, I think there was another question. What card do you recommend to run on your own personal deep learning machine? Do you have any recommendations on which GPU card, unless you want to sell a DGX workstation? Is there a card which you would recommend, Jochen?
Yeah, I mean, obviously, let's go back. Maybe I have some pictures here. So yeah, you want to, okay, I mean, this would be the best, right? If you have this at home, sorry.
Yeah, well, you don't need it's already 100 degrees in here. I don't know if anybody wants to heat their home, at least in the summer here.
Yeah, and it's cool inside, it's really nice. Yeah. So this one is the Selene. It's our own supercomputer, and it's the top two in the top two of the Green 500. So it's very energy efficient also, and holds many records in MLPerf, for example. But maybe more for the end user, you could think about these racks here with the DGX A100. So DGX A100, it's kind of this this box that you see. It has 8 GPUs inside, and all the. It's also important to look at the rest of the hardware. It's not just the GPU, but everything is optimized here to have no bottlenecks, basically. So, and what's really inside here, it's the A100 card, and the A100 is really something that that's very flexible, and it's the fastest and biggest card that we have produced so far. And you can really partition basically the workload, so you can have many workflows on that. For example, you can split it into 7 sub threads here. For example, you can have here TensorFlow training. At the same time, you can have inferencing. So this is really very effective. And yeah, so you can train several models at the same time. So this is really the A100 card is something that is the latest development here, and it's really fast compared to the V100, which is also a great card already, but you can even accelerate that and what's on there. And also it is not just for, let's say, typical deep learning jobs, but also a lot of high performance computing, data science workloads, loading the data. So all this is massively accelerated with A100, basically.
Cool, thank you. So I think we are close to 1 o'clock. I know it's pretty late in the evening for you already, Jochen. Thank you for taking your time and presenting at our summer school. It was very educational. I'm so glad to see not only the theoretical aspects, but also the pragmatic aspects of how do we realize any of these techniques and how do we operationalize AI, because ultimately the frameworks and the research needs to get to a pragmatic level to be operationalized. And in order to make sure we have a cohesive ecosystem of not only just the tooling, but also the research, the tooling, the methodologies, the computing frameworks, and also the hardware to accelerate all these aspects is necessary to make sure that these techniques become more and more prevalent as we kind of deploy these techniques within the industry. So next week, we're going to have another topic on how do we validate deep learning algorithms. And we'll be focusing mainly on algorithmic auditing techniques. And that's going to be 12 o'clock Tuesday, East Coast time next week. And I will see you all then. If you're interested in any of our courses, I put in the link in the chat window, but go to qsummer2021.splashtop.com and you'll be able to know more about that. Thank you so much, and I'll see you in another week. Thank you. Bye-bye.
Thank you, Sri. Thanks for